Welcome to BHARGAV SUBS. So today we discuss the concept regarding uniqueness theorem. So before discussing uniqueness theorem, let us make a clarification regarding what is meant by unique. Okay, unique is nothing but it represents a single value or one value or one solution. Okay, see, for example, in our humans you have your own DNA structure, like DNA internal structure, intermolecular structure. I have my own DNA intermolecular structure. So DNA is unique from person to person. Okay, it varies. It is different for you, it is different for me. As same way, my own style, I have my own style, I am unique. You have your own style, you are unique. Okay, so there is a qualities differ. Okay, so it represents a single value. It belongs to the some a concept, okay, or some structure, okay, or some property. Okay, it is a single value which belongs to the some property. Okay, only that value defined. Okay, only that value exists. Likewise, uniqueness theorem is used in different fields. Okay, what I said just now, like a unique in DNA structure, it is the one field, medical field. Unique in our personalities. Okay, a unique style. Okay, this uniqueness theorem can be defined in many ways, like in many fields. Okay, here this uniqueness theorem we are discussing in electrostatic field. Okay, electrodynamics and electrostatics field. It is helpful in magnetostatics also, and it helpful in problems, solving problems. So in various fields it was helpful. But coming to here, this I am discussing uniqueness theorem in electrostatics, right? So in electrostatics, why we are using this in uniqueness theorem? Because in solving problems, like if you come across a Laplace equations, okay, or Poisson's equations, so to find the potentials, okay, to find the potentials in a surface, or you are given a charged body. So if you want to find the potential, okay, potential inside the conductor or outside the conductor or on the surface of the conductor. Okay, so this Laplace, this uniqueness theorem was used. Okay, and also this uniqueness theorem also used in fluid dynamics also. Fluid dynamics, heat conductions, okay, heat conductions, fluid dynamics, and also calculating the capacitance, okay, designing the capacitors, because capacitor is equal to Q by V. Okay, so Q by V means charge by potential. In denominator you have a potential. Okay, V. What is meant by V? Potential now. So to calculate the V, you will use this Laplace uniqueness theorem. Okay, so if you given a problem to solve the problem, if it satisfies this uniqueness theorem, then you can judge that it will have only one solution. Okay, only one value. So without solving the problem, so without integrating, without using complicated problems, you can easily find that it has a single value. It has if it satisfies the one answer you got, there is no need to find the other value, because it was same. Okay, it was same throughout the body. It was same throughout the body. If at a particular point you got one solution, but if you want further to another point, if you want to find that another point, no need to find, because it has only one value, unique value. Okay, so in electrostatics, how it was helpful, let us discuss. So in uniqueness in electrostatics, generally we have two equations. One is Poisson's equation and one is Laplace equation. See here, Laplace equation is nothing but del square V is equal to 0, del square V is equal to minus rho by epsilon naught into V is the Poisson's equation. So where Laplace equation was used, where Poisson's equation was used. Generally Laplace equation was used when it is in a free space. Okay, free space means there is no charge present. Okay, in the free space, if there is no charge present, charge was 0, charge density was 0. In this case, this in the formula del square is equal to charge density is equal to 0. Okay, here charge density is not equal to 0. Okay, when charge density is equal to 0, del square V is equal to 0. When charge density not equal to 0, del square V is minus rho by epsilon naught V. Okay, so here in a free space, if you want to find the potential, okay, there is no charge in the body, so you will use the Laplace equation. If there is a charge, the given charge, okay, then you will use this minus rho by epsilon naught V. Okay, there are some uses in field of electrostatics. Okay, this is the equation you can use. In fluid dynamics, also this Laplace equation was used. Okay, this Poisson equation was used, where in Laplace equation in fluid dynamics, like if you want, like in fluid dynamics, the laminar flow, you know laminar flow, okay, like flowing in a like different structures, like in laminar flow, this equation was used in fluid dynamics. Okay, and also if in a heat conduction, the temperature distribution throughout the body doesn't change with time. Okay, it is called a steady state. What is meant by steady state? Steady state, the temperature doesn't change with time throughout the body. Like temperature distribution was same while the time changes. If the time changes also, temperature distribution remains same. That is known as steady state. Okay, at that time you will use this Laplace equation. Okay, to solve those problems. Okay, here in Poisson's equation means like in electrostatics, if the charge was present inside of the body, you will use this Poisson's equation. So these are the two equations where we can use in electrostatics. Let us you are considering, because charge density not equal 0, charge density is equal 0. There in fluid dynamics, like there will use volume, like density rho. Okay, density, here charge density, there density, like regarding mass of the body, you will find a density. Here you are considering electrostatics charge, no? So charge density. So here charge density is equal to 0, charge density not equal to 0. These are the two equations you use in uniqueness theorem. So these equations can be applied to the enclosed surface. Okay, these two equations in electrostatics, you will and you are taking a particular enclosed surface. It was a constant, like it cannot increase, it cannot decrease. You are taking a enclosed surface and there you are applying these two equations. Okay, and also what I said, there is a one solution. So that's why uniqueness theorem explains the one solution to the del square V. Okay, it explains that there is only one solution, like del square V is equal to 0. It is a function. Okay, V of R, it is a function. So if you place like a solution to that, you will get 0. Correct. If you got 0, that is the solution. If you place any function, like any value in the function of V, if you got 0, then it is the solution. So that solution is unique, only one value. Okay, so del square V represents a one solution. It represents a one solution, and it can be used in metallic and non-metallic also. But here one condition was there, you can use metallic surfaces and non-metallic surfaces also. But in case of metallic, okay, it is regarding metallic bodies, it is regarding non-metallic bodies. Okay, this uniqueness theorem can be applied in metallic bodies and non-metallic bodies both. But when coming to the metallic bodies, like you can apply both in inner and outer surface also, on the surface also, because there is a charge present on it. Okay, it can be applied both inside and outside. Okay, if you place inside, there is no electric field inside the conductor. Okay, inside the conductor, inside free space, there is no electric field. So in case of no electric field, that it is a free space, so you can use inside. Okay, outside means like it depends on the surroundings. Outside charge was there, outside on the surface charge, which if the charge is present, so it depends on the surrounding charge densities, how the effect of the environment, the charges. Okay, so this metallic body, you can apply both inside and outside this Laplace equations. Okay, for coming to the non-metallic bodies, it cannot be applied inside the body. Okay, it can be applied only inside the body for non-metallic surfaces. Okay, for metallic bodies, you can apply both inside and outside. Correct. But coming to the non-metallic bodies, you can apply only inside the surface. Okay, so to justify this, I will take one example. I am taking a like one bounded body. Okay, one body which has like, see, inside there is no charge, but outside charge density not equal to 0. Inside is equal to 0, outside charge density not equal to 0. So if the charge density is equal to 0, I will use del square V is equal to 0, Laplace equation. If I have dou not equal to 0, then I will use Poisson's equation, del square V is equal to minus rho V by epsilon naught. Okay, so see, if I have, for example, I will give one example. See, if a body was given, in that body, for example, they want to find, they're asked us to find here the value of the potential. Okay, potential V. like they are asked us to show that here it is the potential V naught for suppose. Okay, for suppose V naught. So to show this, no need to do like solution, no need to integrate like taking a part, integrate it, volume integrate, no need to do that. Simply like this, it is a bounded surface. No, it is a bounded surface, so there is a condition, bounded conditions. Okay, so if the given equation, like given function, okay, satisfies this bounded value, okay, bounded equation, if it satisfies the bounded equation, and inside if you got V, the solution for the because you are applying inside, okay, del square V is equal to 0, you are applying inside the value you got V, solution for the Laplace equation. So throughout that body the V remains constant. Okay, no need to find. If you got here, if you got here a particular value, you got the V. So up to here, where you can find this, you will have the same potential. Okay, up to here, like you can see it by using this uniqueness theorem, you can able to answer the question like it is a constant throughout the body. Okay, so like inside the body there is no maximum minimum. Maximum minimum is like two values. Okay, like one is maximum, one is like there is a solution, like one solution it represents, like inside body it is constant throughout a one value. There is no maximum and minimum because charge density is equal to 0. Okay, so I told you like this body will have a constant voltage. Okay, constant voltage throughout the body, it has a constant voltage on the metallic body, like no charge. Okay, no charge, no, like metallic body encloses no charge, no. Okay, on the surface it has charge, like inside there is no charge, no. So a constant value, like no maximum minimum, like there is no like greater value or lesser value, it has a constant value. Okay, so this is the some points regarding the uniqueness theorem, and the uniqueness theorem is the license to imagination. Okay, license to imagination means, see, I told you find a solution, unique solution. I told you to find a unique solution. How you can find? Your wish. In any method you can find. Okay, either by using like integration, either by taking method of images. Method of images means you are taking a imaginary charge, and you are finding that like for total surface. Okay, so in any way, for example, if I want to come from Andhra to Karnataka, in India there is only one Karnataka, unique solution. This is Karnataka is a unique solution. So if I want to come Andhra to Karnataka, either I can come by car or by bike or by train or by flight. My choice. Okay, if you ask me like how I can come, I will come in general by standing. Okay, my wish, my choice. Okay, how I can come, like I will decide. Okay, so imaginary, like imagination. Okay, imaginary means like you can take any way, you can go with any way. Okay, in any way you can find the solution. Okay, either what method you like, in any way you can find, but you will get a unique value that will remains constant throughout the surface. That is the uniqueness theorem. Okay, so the uniqueness theorem is the license to the imagination, like even in any method you can find the solution, you will get a one solution, and solution satisfies the Laplace equation, then it is the solution. Like it satisfies the Laplace equation, then only it will be the solution. And so if charge was present, charge not present, like Laplace equation. If charge present, Poisson's equation, del square V is equal to minus rho by epsilon naught. Okay, and for this theorem helpful in like how many fields, like electrostatic problems. Okay, in solving electrostatic problems, this Laplace equation can be used. Okay, like solving electrostatic problems, like this type of problems, if they want to find the potential, like in further we will discuss some examples. Okay, if there is a chance, we will discuss some examples regarding uniqueness theorem. Okay, so like, and there cannot be any, like if you find one solution, then more than one solution will not possible. Like there cannot be any different solution that satisfy the same condition. Okay, only one solution satisfy. More than one solution, like no need. Okay, only one solution. This theorem exactly says once you find the solution, once you got the solution, it cannot be any different solution that satisfies. Okay, so like it applicable in electrostatics. Electrostatic means like to find the potentials. Okay, to find the potential regarding the on the surface. Okay, it's constant. And magnetostatics, like see, gradient cross B is equal to 0 means what? Gradient cross B is equal to 0 means the vector which represents the field, like vector which represents the magnetic field, will give us a unique magnetic value, will give a unique magnetic field B. Okay, capital B will give a unique magnetic field B equal to 0. Okay, there also you can use this uniqueness theorem. Okay, in that the vector which represents the magnetic field will give us a unique magnetic value throughout the surface, okay, throughout that field. Okay, and Laplace and Poisson's equations I already told, these in this it is used, and also capacitance calculations Q by V. Okay, and also approximation methods. Approximation method means like method of images. Okay, some approximation values will be there, like to calculate the accurate value. Okay, like you want to imaginary something and you want to find there the potential value. So like there are some approximation methods we will discuss. Like so these are the main points regarding the uniqueness theorem. So like next in next page I will give you an exact statement of the uniqueness theorem, and like we will prove the uniqueness theorem. Okay, you understood now like what is uniqueness theorem. Okay, it represents a unique value. Okay, so let us discuss the statement regarding the uniqueness theorem. Okay, so this is the statement regarding uniqueness theorem. So what the statement says, the uniqueness theorem states that, okay, the solution to the Laplace equation, okay, the solution to the Laplace equation or Poisson's equation in a given region, okay, the region was given here, in a given region is unique. Okay, when if boundary conditions are specified. That is a simple statement for the uniqueness theorem. Okay, so the uniqueness theorem says that the solution of a Laplace equation or Laplace equation or Poisson's equation is or in a given region are unique if boundary regions are specified. Okay, boundary conditions are specified. Now what means, like what it means? Okay, potential function. Okay, in electrostatics we have a potential function. That potential function satisfies this given differential equation. Okay, and satisfies the both equations. Like both equations means like both Laplace and Poisson's equation. Okay, so like it is this means the potential V of R satisfies both given differential equation and boundary conditions, and like of the same domain. Okay, of the same domain means like it belongs to the same group. Okay, same region. Okay, so what this theorem applies to electrostatic potential satisfying what Laplace equation and Poisson's equation. Okay, it's satisfying Laplace equation and Poisson's equation. Okay, so del square V is equal to 0, dou square rho is equal to 0, dou square V is equal to 0, dou square V is equal to minus rho V by epsilon naught. Okay, this dou square is the Laplacian operator. Okay, this dou square is the Laplacian operator and V is the electrostatic potential. Rho is the charge density. Okay, rho not equal to 0. This is rho is equal to 0. Okay, rho is equal to 0, rho not equal to 0. This is the charge density, and epsilon naught, permittivity of free space. Okay, 8.8 into 10 to the power of minus 12 Newton meter per coulomb. Okay, so like epsilon naught is the permittivity of free space. Okay, rho is the charge density, V is the electrostatic potential, dou square is the Laplacian operator. Okay, that is the simple statement. That uniqueness theorem states that solution to the Laplace equations or Poisson's equation satisfies the in a given region is unique. Okay, satisfies the given differential equations. Okay, like these are the second order differential equations. Okay, second order partial differential equations. Dou square V equal to 0, dou square V equal to minus rho by epsilon naught. Yeah. Now let us discuss the proof for the uniqueness theorem. Right. So like what is the uniqueness theorem? There is a one solution, correct? There is a one solution. So like before proving that, to prove that like there is a one solution, I am assuming there are two solutions. Okay, I am assuming like I am taking a method called contradiction method, like I am going opposite. Okay, so I have to prove one way. So I am going opposite to that. If it get false, okay, if it get false or if my assumption was wrong, then it will be only one solution. Okay, if you take like one or more solutions, like see, I am taking, let us assume there are two solutions V1 and V2 on the surface. Okay, on the surface means what? Like we have to apply the Laplace equation. Okay, there is no charge here. Charge density is not there. So like what is the Laplace equation? Del square V is equal to 0. Right. So these are the solutions. So I have to substitute that two solutions in the Laplace equation. This is the Laplace equation, del square v1 is equal to 0 and del square v2 is equal to 0. I substituted both. Okay, now I am defining a new function, okay, new potential, okay, another potential. These are the potentials, okay, v1 and v2 are the potentials. These are the potentials we got, okay. I already told you in electrostatics it is used to find the potentials, okay. These are the two potentials, so it satisfies the equation, second order partial differential equation of Laplace. Okay, now I am considering a new potential known as Vd. Okay, Vd is nothing but like difference between the potentials v1 and v2. So v1 minus v2. So Vd is equal to v1 minus v2. Now what I am doing, I am applying Laplace operator on both sides. Okay, here I am applying Laplace operator del square Vd is equal to del square v1 minus del square v2. Okay, I applied. I got 0. Okay, because del square v1 is 0, del square v2 is 0. So 0 minus 0 is 0. This is the first equation. Okay, now, okay, like this is the first equation. Now I am taking another two solutions, v1 and v2. Okay, and like there is one solution. Okay, I am taking a charge, like we have two equations now, Laplace, here up to Laplace. Okay, here up to Laplace. Okay, so from this del square v is equal to vd is equal to 0. Okay, means what? I got like v1 is equal to v2. Okay, v1 is equal to v2. Okay, and now I am considering a Poisson's equation. When we consider the Poisson's equation, if charge density not equal to 0, okay, if charge density not equal to 0, we will consider the Poisson's differential equation. Okay, Poisson's second order differential equation. Del square v is equal to minus rho by epsilon naught, where rho is the charge density. This is not equal to 0. Okay, in that case, again, I am taking on the boundary. Okay, I am taking on the boundary. So again, yeah. So if you take v1 dash and v2 dash are the solutions. Okay, like it is the inside. Okay, it is the inside. Del square v is equal to 0. It is on the surface. Okay, del square v1 dash is equal to minus rho by epsilon naught. And del square v2 is equal to minus rho by epsilon naught, because charge density remains constant overall. Charge, it is a density, like it is like for the whole boundary. So minus rho by epsilon naught, minus rho by epsilon naught, rho not equal to 0. Now same function I am defining again. So vd dash, here I took vd. Okay, here I am taking vd dash. Vd dash is equal to v1 minus v2. I am applying Laplacian operator. So del square vd dash is equal to del square v1 minus del square v2 minus rho by epsilon naught minus, okay, of v2 dash. Okay, v1 dash minus v2 dash. Okay, v2 dash how much? Okay, del square v2 dash. Del square v2 dash how much? Minus rho by epsilon. I substituted. v1 dash how much? Minus rho by epsilon. I substituted. So middle minus was there. So minus is plus. Okay, minus rho by epsilon naught plus rho by epsilon is 0. So up to here, okay, no? Okay, I took the both equations and substituted the solution. I got this. So finally what I got? vd dash. Okay, del square vd dash is equal to 0, del square vd equal to 0. Okay, now I am defining a vector identity. Okay, in calculus I have a vector identity known as, okay, in gradient, like in what we call vector algebra. Yeah, sorry, not calculus, vector algebra. So in vector algebra I have a identity. So del dot vd is equal to, okay, I am applying gradient to vd, like two functions. Okay, so what is the formula? v like outside, v into gradient of d plus d gradient of v. Okay, you understood the identity? Okay, I am applying gradient to vd. Okay, v gradient d plus d gradient v. Okay, now I am substituting in place of v vd. Okay, vd, what I took here. Okay, in place of v vd, and in place of d gradient of vd. Okay, v is vd, d is in place of d, capital D, I am substituting gradient of vd. So let us see what you will get. Okay, so in place of v vd, in place of d gradient of vd, substituted as it is substituted. In place of v vd, d gradient vd, v vd, d gradient vd, d gradient vd, v del v in place of v vd, in place of d gradient vd. Is it okay? In place of d gradient vd, in place of v gradient vd, I asked is substituted. Okay, now this is the equation I got. gradient VD into gradient VD how much? Gradient VD whole square, like modulus. Okay, it is a positive value, so gradient VD is the gradient VD whole square, like modulus square, and gradient into gradient square. Okay, gradient into gradient square, and as it is, like this remains same, gradient of VD dot gradient VD. Okay, del VD, and again this is can be taken as second equation. Okay, so I got first equation, del square VD is equal to 0. Directly I am substituting this 0 value in place of del square VD now here. Okay, del square VD I substituting 0 here, so I substituted, so VD into 0 is 0, so it will disappear, and modulus del VD whole square, so del of VD into gradient VD. Okay, del VD into del VD is del of VD dot del VD is equal to del VD whole square. Again I got this now. Again I am taking volume integral on both sides. Okay, I am taking volume integral on both sides, so I took volume integral here, volume integral here. Okay, this is the third equation. Correct? Up to here clarify? Up to here clarify? Now I substituted directly in the place of identity, I substituted these values, so I substituted 1 in 2 and I got this one. So again I am doing volume integral. Okay, so this is the third equation. And again in vector algebra I have here another theorem called divergent theorem. Okay, so surface integral d bar dot ds bar. Okay, surface integral is equal to the volume integral of gradient of d. Okay, gradient of d vector. Okay, surface of vector of d is equal to surface integral of vector of d is equal to volume integral of gradient of d. Okay, volume integral of gradient of d. Yeah, let us see next what is the next step. So coming on to the next part, so like we got applying volume integral on both sides, we got this third equation, and we know the divergent theorem, like we got fourth equation. This is fourth and this is third. Now what I am doing, applying this divergent theorem. Okay, this is the divergent theorem, like in the vector algebra. So I am comparing these two equations. Okay, I am comparing this theorem with this above equation what we got. Okay, after comparing, here volume integral del, okay, del dv. So what I got, VD into del dv is equal to d. Correct? Yeah, so like on comparing these two, I got d as this value. Okay, on comparing these two I got d as this value, so I am applying this divergent theorem to the above equation. Okay, so surface integral. Okay, what is the surface divergent theorem? This only na. So surface integral d bar dot ds. Okay, what is d here? This one. Okay, so d bar dot ds, so d ds bar. Okay, d ds surface integral is equal to volume integral del vd square dv. Correct? Okay, so I am applying this equation to here. I am substituting, like this is the d value I got, I am substituting in this in this equation. Okay, like I am equating like both. Okay, I am comparing. So surface integral d bar dot ds, d I got here, like is equal to volume integral del vd square dv. So like this is the surface integral, this is volume integral. Surface integral, you know, like you are taking a bounded body, no? So like the bounded body has a radius r. Okay, the radius r, the surface was large when compared to the points inside. Points inside, like what you taking v1 v2. Correct? v1 dash and v2 dash on the surface, v1 v2 are inside the surface. Okay, so after taking v1 v2 inside the surface, after v1 dash v2 are the outside. So after taking v1 and v2, it is a point charge. Okay, those are small when compared to the surface area. Okay, area was very large. Okay, you will get area was large. So like radius was large, very large comparing, like while you are comparing with these point charges. Okay, so while you are going, like you are integrating now surface, while you are integrating the surface from potential, okay, the potential point to the radius. Okay, so while you are going, okay, both v1 v2 can be treated as point charges. Those are point charges, no? So since size of it will be small, like point charges compared to the r, so like surface integral decreases while you are going to the boundary. Okay, while you are going to the boundary, surface integral decreases and approaches to 0. Correct? Okay, you are integrating the surface integral. over the charge bounded body. Okay, so while you are moving to the bounded region, like at the end up to radius r, so here you are getting surface integral, this one is approximately equal to 0. So like approaches to 0, so this is equal to 0, substitute here 0, so this volume integral del Vd square dV is equal to 0, correct? So if I got del Vd square is equal to 0, okay, like this is positive, okay, so del Vd is equal to del Vd square, if you go that side also you will get 0 here, so Vd is equal to 0. What is Vd? Initial we took V1 minus V2, Vd is the new potential, V1 minus Vd is equal to 0, so V2 is equal to V1. Okay, I am taking initially two values, okay, see, after taking two values I got both are equal. After deriving all this I got both are equal, means what is the point of taking 2 points? I can take only one point, which is a unique solution. Both are equal, so both are equal, and those are not two different solutions. Okay, those are not two different solutions. These are same solutions. Okay, V1 V2 are the same solutions, like same value. Okay, same solution for the Laplace or Poisson equation. Okay, so like according to unique theorem there exists a unique solution. That's it.